Welcome back to another LeetCode video. We've just checked off the palindrome partitioning problem of our bucket list. We're using LeetCode.io to go through all of the backtracking problems that are part of the LeetCode 150 list, which is an extension of the Blind 75 list, which is a curated list of LeetCode problems that show all the patterns that you should know in coding interview. So we have two more problems to go today. One is letter combinations of a phone number, and the other one is n queens. I have not looked at this before, but maybe I've solved it before. I don't know. Let's see. I've solved it before. My last submission was 2 years ago. So let's see what we're dealing with here. Hopefully I can solve it again. So given a string containing digits from 2 to 9 inclusive, return all possible letter combinations that the number could represent. Return the answer in any order. Okay, also possible. Okay. A mapping of digits to letters, just like the telephone buttons, is given below. Note, 1 does not map to any letters. Okay. All right. Constraints. Well, the length of digits. Wait. We're given a string containing digits from 0 to 9 inclusive. So that's this thing. Digits. So the length of digits is either empty or maximum 4. We don't really care about the max because a fixed max will mess up our space and time complexity analysis. Everything collapses to be constant space and constant time. But what is interesting that the digits are in the range from 2 to 9 because the 1 does not map to anything. Yeah. Cool. So let's check out an example. So digits 2, 3. What are all the letter combinations? So 2. Okay, so we could choose A, B, or C for the first letter. A, B, 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 or C, C, C. And then for the second letter, there's a 3, all the, or D, E, F. So we combine A with D, E, F, B with D, E, F, blah, blah. Okay, I see. And if digit is empty, we just return the empty list or empty array. If we only have one digit, then we just list all the combination of letters that fall under that digit. Okay, cool. All right. Yeah, I think this is very doable, but we'll have to do some coding to put this into code, this mapping. And all we need to do is we need a little helper function where we select the next digit, and then we iterate over all of the letters that are associated with a digit and build up our little solution strings here. So we pick the first one, the first letter. Well, we'll have a recursive helper like we do in all of these backtracking problems. Maybe I should just point that out real quick. So we have a helper method. That one should have an index that tells us from which digit to continue. I call it IDX. That's a new cool way of how to write index. It's better than I and shorter than index. And we also need to know what is the current string, right, that we've built up. So, and I sometimes like to use the variable name path because we're kind of path finding through this thing, right? Now the first position on the path might be then A, B, or C. The second might be then a D, E, or F. So we'll have a path, and we need to have a condition for when to end. So that will be if IDX larger or equal than length digits, right? Then there's a case we need to add the current path to our result. Result.append path, and we need a copy of the path. Well, actually, since we're returning strings, I'm already in the middle of the implementation. I'm sorry. Join path. So we're joining all of the characters that we collect to a string. Now, result is where we store the result. We define it outside the helper function. In the end, we return the result, but we also have to call the helper function. Helper, we start at index 0, and we have no path. How to manage that with the result is up to you. You can also just put it in here. I think I've mentioned this now in every backtracking video. Doesn't matter. Just do this. Return result. It's just easier to have it outside in the beginning when you start to write your code, so you don't have to take care of passing it and blah, blah, blah. But anyway, so this is kind of the scaffolding for our backtracking recursive thing. Now, what we have to do now is we have to figure out what is the current digit, right? Digit equals, well, it's digits at position IDX. That's the current digits. And now we need to iterate over all of the letters that belong to that digit for letter in, well, we need a mapping. That's what I said, digit. And we need to choose then from the mapping. And we have to create that mapping here in a second. We basically have to transfer this image into Python code, I guess. And then what we do is we just look up what are the digits that are the letters that are mapped under that digit. So if we say, okay, A, what letters? Oh, sorry, 1 doesn't have any. 2 has, well, what letters? Well, A, B, and C, right? That's what it has. Now 3 has something as well. 4, 5, 6, 7, 8, 9. They all have something. So ABC, EF, GHI, GHI is correct. GHI, JKL, MNO, PQR, PQRS. So there's an outlier here. 7 is mapped to 4. EUV and YX, W, X, Y, Z. Okay. So that's basically the mapping that we need. So this is the hash map. So now we can grab the digit from our input string and directly map it to all the letters. So what we do now is, well, we're going to append the letter to our path. Then we do the recursive call, and after, we want to pop that letter off, because in the next iteration of the loop, we're going to add another letter. And we don't want to add A and B to our result, right? We want to add A or B. So, and then we do helper. At X, we're increasing our index. We pass in the path and the result. And that should be everything. Yeah, that should be everything, really. So now, in terms of runtime and space complexity and space, so the space, well, we have stack space. That's one thing, right? So how deep does our recursion go? Well, it depends on how many digits we really have. That's what it depends on. But, you know, it only depends on that, right? And we say n is len of digits. That's the stack space is O of n, but we also have what we need to store the results. And that is actually, well, what is the average branching factor that we have? I would say it's 3, even though we have like 2 4s in here. 2 where the letters 4, we have n to the power of 4, I would say, don't we? Because at every step, for every digit, we have 4 choices. Was it 4 to the power of n? Yeah, I'm not that good with these. I have to study this. Maybe I'll make another video where I explain that. But right now, I'm kind of guessing my way through this. But that's okay. I'm just practicing. Now, in terms of time complexity, what do we have? Well, kind of the same thing, right? But I remind myself that in every decision we can either pick a letter or not. That's a binary decision. So, and since we're iterating over only a constant number of characters in the mapping, I think the runtime complexity would have to be 2 to the power of n, right? and space probably as well. I'm not sure. I don't know. Let's just test if this works, and maybe we can look up what other people say, what the complexity is. Right, so we have to append the letter here. There's an error. Why is there an error? Mapping. String index out of range. Well, mapping. For letter in digits of IDX. Aha. We are missing the else. That's very important. Otherwise, even if we are over the length, we will run into out of index errors. Wrong answer. Oh, we return an empty list. A list with an empty string. Okay, so that means we need another statement if path. If we don't have a path, then there's nothing to add. Right, so that passes all of the test cases. That is nice. Let's submit it to see if it passes the final tests. It doesn't. Okay, why not? Output digits 5. So that means I probably have an error in the mapping. So we put I, but it should have been a J. Let's look at the description. GHI, and we have I twice here. So there's an error in the mapping. I'll try it again. Okay, now that works. Let's see what do people say with solutions. Simple solution. Somebody who makes a video probably should put in the effort to also do the runtime and space complexity analysis. Okay, same mapping idea. Right, I think that's exactly the same idea that we have. Except this dude is creating a new string every time. So he's not being as smart, where he just uses a list. So this is an O of N operation every single time. So that is not good. Maybe it's good, but not the best. I don't want to throw shade on anyone. So 4 to the power, 4 to the n. Wait, that's what I said. And space complexity for the recursion call. Yeah, but that's wrong because we already figured out we have less recursive calls than we can have results in the end, right? Well, no, wrong. The depth of the recursion is not the same as the number of times that we hit this case in a recursion. So that is, I don't think that is correct. It can't be correct. You know, if we have 3 digits, doesn't mean we have 3 results. It means we have 4 to the power of n results. Or 3, if we assume that this is the, well, 4 is probably a good upper bound. You know, if everything is 9, that's the worst case, then that's how many results we will have. And yeah. Anything else? I'm surprised how nobody really has a good explanation for the runtime. Maybe everybody keeps skipping that. So this one says n, but I don't think it's n times 4 to the n, because so if you do n, I believe that means you iterate through n. Actually, we do. No, we don't iterate through n things in our loop. We only iterate through a constant number of things. That's why I think this n has to go away. But I'm not 100% sure, but we've solved this problem, which means we can tick this one off. And next time we're going to tackle this one.